Choosing an orbit is not a matter of preference. Every kilometer you add between the handset and the spacecraft costs link budget and latency, and both have to be paid back somewhere. In this lecture, we work out why broadband direct-to-device converged on low Earth orbit, what that choice costs, and how constellation geometry decides whether the network actually works. Start with the direction everyone forgets. The downlink, satellite to phone, is the easy half. The hard half is the uplink. A standard handset is a 3GPP power class 3 device, about 23 decibel milliwatts, 200 milliwatts, through a small low-gain antenna, built for a tower a few kilometers away. A conventional satellite terminal transmits several watts through a directional dish. The spacecraft has to detect that weak phone signal from hundreds of kilometers up. In practice, the uplink, not the downlink, decides whether the link budget closes. Distance is the enemy, and the arithmetic is unforgiving. Free space path loss is 32.44, plus 20 log of frequency in megahertz, plus 20 log of distance in kilometers. Hold frequency constant, and distance becomes the only variable that matters. Against a 550-kilometer reference, medium orbit adds 23.3 decibels, and geostationary adds 36.3. 3 decibels halves your received power, so 36 decibels is a factor of roughly 4,000. For a phone already at its limit, that is not recoverable in software. Latency points the same way. Delay is distance over the speed of light, and a transparent payload puts 2 space legs in each direction. From low Earth orbit, one leg is about 1.8 milliseconds, user to gateway about 3.7, and the round trip roughly 7. From geostationary orbit, that same round trip is 477 milliseconds, nearly half a second before the network has processed a single packet. Random access, HARC, timing advance, power control, and scheduling all assume far shorter loops. So low Earth orbit wins, but it simplifies nothing. A satellite there travels at 7.5 kilometers per second. It rises, crosses the sky, and sets within minutes. That motion buys you rapid Doppler shifts, continuously changing propagation delay, beams sweeping across the ground, frequent handovers, and gateway switching. Instead of one stationary base station, the user is connected to a base station moving faster than a rifle bullet. Release 17 did not remove that physics. It taught the protocols to live with it. Next, a distinction that matters more than it sounds. A satellite at 550 kilometers has geometric line of sight to a circle thousands of kilometers across. But geometric visibility is not usable coverage. Near the horizon, the slant range grows. Path loss rises. Phased array scan loss eats your beam edge gain. The signal crosses more atmosphere, and terrain, buildings, and the user's own body get in the way. Real systems therefore impose a minimum elevation angle, often between 20 and 40 degrees. Altitude is the first design variable, and it pulls both ways at once. Go higher, and each satellite sees more of the Earth, stays visible longer, needs fewer handovers, and you need fewer spacecraft for global coverage. Go higher, and you also pay more delay, more path loss, less uplink margin, and less capacity per unit area. Go lower, and the link closes easily, but each satellite covers far less ground, so you need more spacecraft and more orbital planes. There is no universally optimal altitude. Now, the misconception about mega constellations. Performance does not depend mainly on how many satellites you have. It depends on how they are distributed. Put 1,000 satellites in one orbital plane, and large regions still suffer long coverage gaps. Spread the same 1,000 across evenly spaced planes, and service improves dramatically. Right ascension of the ascending node sets how planes are distributed. Inclination sets the latitudes reached. That distribution drives revisit time. Emergency messaging can wait minutes, voice and broadband cannot, which explains why the market looks so divergent. AST Spacemobile concentrates capability in the spacecraft. Very large phased arrays and high gain beams, broadband from each satellite. Starlink Direct to Cell distributes capability instead, leaning on the scale of an existing constellation and sophisticated beamforming. Link Global lowers the requirement, starting with low rate messaging that tolerates intermittent availability and needs far fewer satellites. Three different architectures, one equation, 3 points in the same design space. To close, the smartphone uplink is usually the limiting direction. Low Earth orbit buys link margin and latency, and pays for it in motion, Doppler, and handovers. Altitude trades link margin against footprint, dwell time, and fleet size, and constellation geomy.